Okay, thanks for the organizer inviting me. And my name is Zheng Cui. I'm the head of Printable Electronics Research Center at the Zhao Institute of Nanotech. The center was established in 2010, so now it's almost 10 years. And at that time, it was the first research center in China to focus on printable electronics research and development. And over the nearly 10 years, we have built up a big group. We have now 75 researchers and over 2,000 square meters of lab space and quite amount of equipment. We also have the engineering center to develop some pre-products technology. Because we have a big group, so we cover quite a wide range of research topics. And from the material, the ink, we make our own ink from organic to inorganic, and we develop our own printing process that including the inkjet printing, screen printing, gravure printing, even the roll-to-roll printing. And we also have a group develop this printing equipment, particularly the inkjet printing head. On the application side of printable electronics, we focus on 4 areas: the photovoltaic and thin film transistors, organic light emission, and flexible wearable electronics. We also work on the encapsulation of organic electronic devices, and our aim is to develop the technology into early stage of product, eventually going to the industry. But today, I'm going to focus on this part of work, the thin film transistor, that including the ink for the thin film transistor, also the printing process. It's good that this morning Professor Nathan also talked about the thin film transistor, so I'm going to come back to the topic again. So that's the outline of my talk, and first introduction, why we do the inorganic instead of organic. And the work we focus on the inorganic, it's mainly the carbon nanotube TFT and the metal oxide TFT. Then I go back to the main topic with this talk, is the CMOS inverter. We have a different way to make the CMOS inverter, basically making the transistors which are complementary. That's including the CNT only, the carbon nanotube only, or the hybrid of carbon nanotube and the metal oxide. And also, we have some recent work on the NMOS inverter using metal oxide only. So finally, the summary. So let's look at the thin film transistor. Conventionally, we know the silicon transistor is always rely on the substrate, where you dope the silicon to generate the semiconducting channel. But for the thin film transistor, everything is added on. So it's additive fabrication, where all the electrode, the semiconducting, the electrical is added to the substrate. So the substrate can be plastic, glass, and even paper, as this morning we've heard. And the fabrication process can be is additive, so can be evaporated or even printing. So that's the printing is the focus of my talk today. Well, in terms of the material, the thin film transistor basically have 2 categories. One is the organic, including small molecule or polymer. Another, the inorganic, we know that's a amorphous silicon, polysilicon, metal oxide, carbon nanotube. These 2 parts is going to be the work we are going to talk about today. In terms of fabrication, the thin film transistor can be fabricated either by the vacuum process, which includes the sputtering, like the metal oxide, you need a sputtering, or the organic transistor small molecule, you need evaporation, or the solution process. The solution process includes coating, where you have the coating the film, then you use the photolithography to get the pattern, or you directly use printing to get the structure of the thin film transistor. And why we use the inorganic semiconductor? Let's look at first the organic semiconductor. We know that the organic semiconductor have a number of advantages, and the first is the designability of organic molecule. So there's a recent report showing that by the August 2018, there's a total 1,682 organic semiconductor molecules has been synthesized. And it's found that 94 of them have the charge mobility over 1, which is better than amorphous silicon. So for this data, you can see the designability of organic molecule is almost infinite. You can still come up with new molecules. That's still the very active academic research area, a lot of people published. So that's the main advantage when we go for the organic semiconductor. And also the organic semiconductor, low annealing temperature, better flexibility, and better printability if you use the polymer material. But the disadvantages are also quite prominent. The primary disadvantage is the low charge mobility and also the poor environmental stability. And if we go for the big polymer, there's a battery-to-battery inconsistency. Also, if you use a smaller molecule, its printability is also an issue. So the main problem with the organic semiconductor is the low charge mobility and the poor environmental stability. So let's look at the inorganic semiconductor. And we know that they have inherited high charge mobility. The typical example is silicon. And because the inorganic is environmentally very stable, it's a material manufacturing technology, abundantly available, and battery-to-battery consistency. But the problem with the inorganic, if you want to print it, so it's difficult to make the ink, and that involves the separation, dispersion, and also if you use the dispersion, the impurity, you have to use the surfactant, which become impurity. Then you have to use the high temperature annealing to get rid of this impurity. And also, once you made the ink, you always have to go back to solid. So by sintering process, you can turn the ink into solid, but the property is no longer the same as its bulk material. But the main advantage is the inherent high charge mobility and environmental stability. That's the opposite of the organic semiconductor. For example, comparing the organic conductors, the P.PSS and the inorganic silver, they have 100 times difference in conductivity. So that's the reason that we prefer the inorganic semiconductor. And how to make the ink? We just mentioned it's difficult to make ink from inorganic material. There's basically two ways to make inorganic ink. First is start with the precursor solution. And there's quite a wide range for salt material where you can dissolve the salt, the inorganic salt into solvent. And you print the salt solution. Then you use the sintering process to recover the solid material in the film. And there's another way, that's a simple start with the powder, and you disperse the powder into solvent or aqueous solution, and you use the additive to change the viscosity, surface tension, then you get the ink. So, for example, this is the silver ink. This is the start with the precursor solution, so it's transparent. You can't see any solid material. But this is by the dispersion, where all the particles inside the solution is not transparent. And fortunately, we have the nanomaterial. We know that the nanotechnology is the biggest the achievement. We have the number of nanomaterials like a carbon nanotube, graphene, nanowire, even the quantum dots. And previously, if we want to use the nanomaterial into devices, you have to use the single entity or the single nanowire, single carbon nanotube to make devices. But this we know that's difficult, cannot be mass produced. But how about we make it ink? We know the nanomaterial always in the form of a powder, and we can use the previously mentioned method to make it into ink. Then we can print it. In this way, we can do it in the industrial scale. But in fact, if you look at this graphene, the most successful commercial product of graphene is making the graphene powder. Then you print it. That's the way to utilize the nanomaterial. And if you look at the printed electronic development, this is the paper published over the last 20 years. And there's the significant increase of the paper after 2010. And we guess, and the main reason, actually the main reason is that inorganic materials start to be used as ink to print it, which stimulates the development of printed electronics. The most prominent example is the silver. We use the silver nanoparticle to make ink, then you can print a wide range of conductive circuit. So let's look at the work we have done. And first, I'm going to introduce the work we done on the thin film transistor. As I mentioned, it's mainly the carbon nanotube and the metal oxide. For the carbon nanotube, for the thin film transistor, we on the semiconductor side, we focus on these two materials, and we use the spin coating, deep coating, Dr. blade coating, drop casting, indirect printing, isotope printing. We use all sorts of solution technology. For the electrode, we use gold, silver, copper, ITO, and the method is the technology to make the electrode, including thermal evaporation, lithography patterning, and inkjet printing. For the dielectric, we use simply the silicon dioxide and the aluminum oxide, hafnium oxide using ALD, and even the iron gel organic polymer. And the way to use them either is PCVD, ALD, or simple inkjet printing. Okay, let's look at the first carbon nanotube. We know the carbon nanotube always is the mixture of metallic and semiconducting. If you use the carbon nanotube as a synthesized, there's a lot of metallic tube as the red line indicate. When you make the transistor, you don't have a very high on-off ratio because all the metallic tube become a conducting path. Then you cannot switch off effectively for this transistors. So we have to get rid of the metallic tube to make it as pure as possible, only semiconductor tube, so that you can make a good transistor. And there's a different way to purify the semiconducting carbon nanotube. The way we do it is to use polymer wrapping. We choose some conjugated polymer, and this polymer has the special property. They can selectively wrap up, or they can recognize semiconductor tube, only wrap at the semiconductor tube. And then you have the mixture of the ink. Then you use the centrifugation to get rid of the metallic tube because the metallic is not wrapped up and they cannot dissolve in solvent. Then you end up with the semiconducting carbon ink. So that's the way how we do it. We bought the semiconductor tube and we mixed it with the solvent and added this special polymer, and we use the homogenizer to make this process happen. So in the homogenizer process, the wrappings take place. Then we use the centrifugation to filter out the metallic tube, so all the semiconductor dissolve in the solvent, and the metallic tube becomes sediment. Then you take this part, that becomes ink, then we can print the transistor. We discovered quite a few polymers which has the property to selectively wrap up the semiconductor tube. We also developed our own polymers to wrap up. So this is the molecular simulation showing the wrapping up the process, and this is the spectrum showing that the metallic tube has been removed. So then we have the ink. Then we use inkjet printing to make the transistor. And the inkjet printing, mostly the printing the carbon nanotube. This is the bottom gate, this is top gate, and that's how it's done. We make the electrode, then we use the inkjet printing to deposit the carbon nanotube between the source and drain, and that's the distribution of a randomly distributed carbon nanotube network. And this is actually the electrode that you have. This is the gate, and this is source drain is the single carbon nanotube transistors. And we do have the thin film transistor which behave like a transistor. So that's the transistor. We have the on-off ratio of 10⁶, mobility around 10, and the highest we can get over 100, and also a good on-off ratio, which allows us to build a circuit. So that's the simple NOR gate circuit, logic circuit. That's the black part actually inkjet printing the silver electrode to connect the different transistors to make it a simple circuit. And we also work on the metal oxide, and for the metal oxide, we focus on the IGZO, and this graph showing that we use a self-aligned process which we inject printing the metal oxide ink. It allows the ink only distributed inside between the source and drain electrode, because we make it both sides are hydrophobic, only the channel is hydrophilic, so the ink can be concentrated on that channel. And we get good mobilities and the threshold voltage, and these are working truly like transistors. We recently also working on the heterojunction TFTs. We know heterojunction can have a very good properties. We also using this self-aligned process. First, we printed indium oxide, then we printed IGZO ink on top of ink oxide. We define the channel by the hydrophobic and the hydrophilic, so it only overlap on the indium oxide. So in this way, we can build heterojunction transistors with perfectly aligned heterojunctions. And this is the comparison using that heterojunction is much better than the single component of metal oxide. It gave you the good performance of transistors. So that's we also work on the larger array transistors. It's a 64 by 64 carbon nanotube, and we have average mobility of 11, also good on ratio. We also made a 64 by 64 IGZO TFT, which have average mobility of 12. And we even use the array to drive the OLED, which there's a uniformity issue, but they are working perfectly fine as transistors. So let's come to the CMOS inverter. We know that CMOS you need a P-type, N-type, and but unfortunately the organic transistor is only good at P-type. N-type is not very good. The carbon nanotube is only good at P-type, and the metal oxide is only good at N-type. But for CMOS inverter, we need both N-type and P-type. So we have a different way to make the P-type or the N-type transistor and to make it the CMOS inverter. So here I'm going to introduce the way to make the carbon nanotube transistor, which normally the P-type, then become N-type, so make the transistor, the CMOS converter. Also the hybrid CNT and the metal oxide, and also some NMOS from the oxide only. So we have three different ways to turn the P-type, normally P-type semiconductor transistors into N-type. The first way, or first scheme, that we use a different polymer to wrap up the carbon nanotube, so that when they print it and cover it with carbon oxide, the different ink appear to be different type. It can be P-type and N-type. So in this way, we have made the P-type, N-type from different ink. You can see that the characteristics, they are truly different polarity of the transistors. So that's the three-stage printed ring oscillator using both P-type, N-type, and it gets quite a good performance. And most importantly, you can get a very low power consumption. That's the topic of I'm giving today. So you can see at a near off stage, you can have near less than nanowatts power consumption for this CMOS converter. And the other way, the second way to convert the N-type is that we use the particular zirconium component and plus the S-SWCNT and to print onto the normally P-type carbon nanotubes. So first we print all the P-type carbon nanotube into the channel, then we select to print this solvent, this material into the some of the P-type transistor, and it become N-type. So that's you can see the different type of transfer curve. And also this is the inverter we made, and this is the N-type, that's the P-type, and this is the printed the electrode connected into the inverter, and you can see the consumption, the power consumption at the near state, also in the nanowatts regime. And the third way we make the P-type into N-type of carbon nanotube, we use this particularly we call chemical doping. This particular TEOA material, when we deposit it onto the carbon nanotube, it gives the chemical or change the polarity of the carbon nanotube into this called the bipolar. So when I have a different voltage, the carbon nanotube appear to be bipolar. So for the bipolar transistor, we also make the inverter. That's the same carbon nanotube, but with chemical doping, we can make the bipolar that's connected with inkjet printed electrode. So that's showing that at the neo state is also very low the power consumption. And also for this one, it's not quite environmentally stable, so we cover with aluminum oxide, and it gave also this the ambipolar the CMOS inverter, where it has a very low power consumption. So let's come to the hybrid. We know that the metal oxide are always N-type, and the carbon nanotube P-type. But unfortunately, normally the metal oxide has had very high controlling voltage compared to the carbon nanotube, only few watts or less than 1 watt, and this is the tens of watts. So we first need to change this metal oxide to match the carbon nanotube, so they can become a pair to be in the CMOS inverter. So the way we do it is two methods. One is we reduce the electrical thickness. Normally this one is 300 nanometers, the dielectric reduced to 50 nanometers, which significantly reduce the voltage. And also we use the different ink. Instead of IGZO, we use IGZO, which tune the mobility similar to the carbon nanotube, also a similar subthreshold swing. So in this way, we have fairly matched the N-type and the P-type transistor, and we make the inverter. So there's a two ways to make the inverter. First is the bottom gate, where you make the metal oxide transistor, the carbon nanotube transistor, then we use the printing to connect them. Then this the inverter, the gain, and this the power consumption about 4,400 nanowatts. And we also made a set gate CMOS, where we use the iron gel as a dielectric using the set gate to control both the transistors. So that's the printing process. All the electrodes made by normal lithography, but the semiconductor is done by the printing. Also, the iron gel is done by the inkjet printing. So that's the characteristic of the inverter, where this is the gain, and this is the power consumption, about a microwatt. So it's not as good as the carbon nanotube inverter. But recently, we have work done using the single junction metal oxide and the heterojunction metal oxide. We have both the technology, and this is the way to make the transistor. You can see that these two metal oxide, we use inkjet printing to connect these two. And the way they make NMOS transistor, because they have a different characteristic, we use the difference to construct this inverter. And this is showing the power consumption. You can see it's also in this the near off state is less than nanowatt, and it's showing that it really can have a very low power consumption of the transistor. So in summary, I'm showing that the printed inorganic TFT offer really high performance and a high environmental stability. Also, showing that a different way to convert the P-type CNT transistor into N-type. And also, I showed heterojunction TFT, and which gave you the oxide TFT give a much better in performance. And we showed a different way to make N-type, so that you can construct the CMOS inverter, which gives you the low power consumption from microwatts to sub-nanowatts. So finally, acknowledgement. This work is really done by one of our team leader, Dr. Zhao, and a successive student from 2011 until now. There are many years of work accumulated. We also have funding from different funding agencies. So thank you for your attention.